talking about this thing called empirical formula. And that's what we're going to talk about today. We use percent composition of each substance. And we look at that to help guide us to get a formula. And once you have a formula of a compound, especially if you're looking for like unknown substances, once you have that formula, you can start doing some other analysis, and you can finally come up with a structure. And when I was in grad school, the lab that I worked in, all right, that was a goal of the lab. They were looking for new, novel compounds in certain plants that would help fight diseases. All right, so we would get all these leaves and roots from plants. We would make extracts of those to get all the compounds out of the leaves and the roots. Then we would start running a lot of different tests to see how these extracts worked against certain diseases. We were looking at things like staph and, what else were we looking at? Staph's the only one I can remember off the top of my head right now. But we were looking for new compounds, so we get these ones. We find an extract that had some what we call efficacy, where it would hurt or inhibit certain diseases that we were looking at. And then we would go and progress from there and run more tests to finally get down to a chemical formula to start looking at structure. Once we found a structure, we could then start looking to synthesize it from there. So guys, empirical formula plays a huge part. Who can tell me what empirical formula is? It's a former vocab term of ours.
It's a formula. The symbols for the elements combine the compound subscription, the smallest number, mole ratio.
It's the simplest formula, guys. It's right there at the bottom of page 6 in your notes, where you're supposed to be. It is the simplest formula, guys. And really, guys, a little bit more detail is the simplest whole number ratio. All right? Simplest whole number ratio. Maybe we want to add that in there. Simplest whole number ratio. Okay, it's something important. We're not going to have decimals, okay, in our subscripts. That's impossible. We can have part of an atom. Okay, so it's the simplest whole number ratio. So there's a process. What we're about to do, guys, there's only really one, maybe two new steps that we're adding. Everything we've done so far to this point is kind of coming together in these problems right here. All right? So there's steps you've got to follow. If you skip steps, that's when these problems become very, very difficult. All right? If you skip one of them, there's one step in particular that a lot of students will forget to do, and then everything else is messed up from there. But we'll see how that is. So here are our steps to get to where we need to be. What we're going to do is we're going to assume that we're always using 100% of the sample. Makes sense. So if we're given percentages, we turn them to grams. Then what we need to do, once we have grams, we will turn it to moles. How do we go from grams to moles, folks? Molar mass is what we're going to use. And what we're going to do to that, we're going to do what with the molar mass? Divide by the molar mass to get there. Once we have the number of moles, then we're going to find the simplest ratio between the elements using the smallest number of moles. And then, if need be, we will multiply to get rid of any fractions, any decimals we have. We won't really round here. Now, what I just read to you, that probably makes absolutely no sense, right? You're like, what's he talking about? We're going to jump right into a problem, guys. We're going to take it step by step. And you see, oh, this really isn't as bad. It seems probably a lot of craziness right now, but it's not going to be that bad at all, you're going to see. So here's our first example. It says a compound is 78% boron and 22% hydrogen. What is the empirical formula? So our first step is we're going to change percent to grams and find moles. So, first things first, guys, with any word problem, what do we always do? Write down our given. So, same way as before, let's write that down. I've got boron. I've got hydrogen. I've got 78% boron, and I've got 22% hydrogen in this compound. It's all we're given. So we're going to figure out the empirical formula just from these two percentages. So step one is we need to go from percent to grams. Make sure you are paying attention. You are watching clearly. Do not blink. This is the most important step. It is one of the hardest things we do all year. Right? I don't have to repeat myself. We want to make sure we get this step down, because if we don't have this step, everything else is going to be messed up. All right? So make sure you are watching. We need to go from percent to grams. This is the process that we will use. So, to get from percent to grams, we do the following. There it is. That's it, folks. It's a joke, all right? Man, tough crowd. Percent to grams, guys. All you do is you just take that percent symbol, you just make it a G. That's it. Because it's based out of 100%, guys, so we're going to say it's 100 grams. It's the same ratio that we had to begin with. This is if we're given percentage to start. If we're only given grams, do we have to change anything? No, we just go with what we have. So hydrogen, how many grams do I have? All right, it's a ratio. It's a percentage. They're in the same ratio. Now, when we go from grams to moles, guys, again, you already told me, what do we use to go from grams to moles? We are going to end up dividing molar mass. All right, so this is where it becomes crucial, guys, that you actually put in the element in your problem. We've got two different elements that we're looking at. So for me to be able to see your work and for you guys to follow it after you get to the end of the problem, you need to make sure you put your substances element in there so you know what you're dealing with. So I've got grams of boron, I've got grams of hydrogen. All right, where do grams have to go to cancel out? On the bottom. What's going to go on the top then? Moles. How many moles do I have in there? 1 mole always, right? 1 mole of boron equals how many grams? Where did I figure that out? Periodic table. How many grams is boron? 10.81. All right, hydrogen, same thing. Grams of hydrogen on the bottom, moles of hydrogen on the top. 1 mole of hydrogen is 1.008 grams. So go ahead and do the math. All right, how many moles of boron are we working with here? 7.22. Go to 2 decimal places, guys. These are the types of problems. If you round too soon, the last steps may be off, which means your final product will be off. So 2 decimal places is a good place to go to. So we have 7.22 moles of boron. Hydrogen, how many we got? 21.83 moles of hydrogen. So guys, there's step 1 and 2. Right? So percent to grams and then grams to moles. Have we done anything new yet? No. Okay, this is all review. Not too difficult at all. 1-step problem. So our next step, guys, is we're going to divide all the mole numbers to get this by the smallest to get our ratio. So I'm going to rewrite my results here so I have space on this slide. I've got boron. I had 7.22 moles of boron here. I had 21.83 moles of hydrogen. All right, so now I'm going to look at all of them. If we have 2 elements, guys, or if we have 15 elements in the compound, we're looking at which one is the smallest number of moles. What's my smallest number here? 7.22, which is boron. So I'm going to divide boron by itself, 7.22 moles, which is going to equal what? 1. Okay. And hydrogen, I'm going to do the same thing. I'm going to divide it by 7.22 because it's the smallest. All right, so when you do that math, 21.83 divided by 7.22, what do you get for an answer? 3.02. So 3.02, guys, it's not exactly 3, but for our purposes, what are we going to call that? 3. All right, so we're going to call that 3. So right here, this is my ratio. How do I write a ratio out? Dots, right? So 1 to 3, right? So that would be the ratio of boron to hydrogen is 1 to 3. How do you think we show ratios in chemistry, though? What do we call those? Not fractions. We do. I mean, we've done all the math here, so we're not going to have a fraction here. Think about it, guys. I'm trying to get to what? My whole purpose in this problem is to do what? Look back at the original question. Find the empirical formula, guys. A formula is a ratio. What's my formula going to be for this compound, do you think? Yeah, so what's my formula going to be? B3H? BH3, right? Because, guys, we take the numbers, these numbers that we get here from our ratios are telling us what our subscripts are for the compound. We have BH3. I'll give a prize if you can raise their hand and tell me the correct name of this compound. All right, so to get that compound, 1 new step, really the last thing, guys, we've done grams to moles. Easy. The last new step, right, is to divide by the smallest number of moles to get a ratio between them. That's all we're doing. Let's do another example here together. All right, I already wrote that in there. Our final answer was BH3. All right, here we go. Example number 2. Analysis shows a compound to contain 26.56% potassium, 35.41% chromium, 38.03% oxygen. Find the empirical formula for this compound. First things first, from a word problem, what do? Write down what we know. So we've got potassium, we've got chromium, and we have oxygen. Folks, do I really need to write down the percentages there? No, what should I just write them as? Just make it grams, right? Save yourself some space. 26.56 grams of potassium. We've got 35.41 grams of chromium. And we have 38.03 grams of oxygen. So that's the first one. Now, second step is to do what? Get to moles, all right? Because, guys, we can't compare grams. Why can't we compare grams of substance? We already talked about that this week. Why can't we compare grams of one to another? Why do we have to get to moles? Do all elements have the same mass? No, right? They're different sizes. So because they're different size atoms, mass is not a true reflection of how many particles we have. We are looking at the number of moles, which is why we've got to do this. So go ahead, calculate each to get the number of moles. We're going to divide by their molar masses. The molar mass of potassium is what? 39.10. All right, and then 1 mole of K on top. Grams will cancel out. Chromium, what's its molar mass? All right, grams will cancel out there. Oxygen, we all know that one by now. 16.00 grams of oxygen. That will cancel out. So, when we do our math, who can tell me how many moles of potassium we have? 0.68 moles of potassium. What about chromium? How many moles do we have? Same. 0.68 moles of chromium. And then oxygen, when you go ahead and do the math, when you divide those, you get, should be a different number this time, 2.38 moles of oxygen. All right. That's kind of my first two steps right there. Percent to grams, grams to moles. When I have everything in moles, guys, and this is the step that most people forget about. All right. When I have everything in moles, what do I have to do next? You've got to find the smallest number of moles and divide just one number by that. All of them by the smallest. So I'm going to rewrite my results right here. I've already converted to moles. All right. So I get 0.68 moles of chromium, 0.68 moles of, I'm sorry, chromium was the second one, potassium was the first one. And then 2.38 moles of oxygen. So what's my smallest number here? Yeah, I'm going to divide everything by 0.68. So the top two are really easy. They are what? 1. All right, so K equals, CR equals, and O equals. So when I divide the last one, I divide oxygen by 0.68, what number do I get? 3.5. All right, now, in our last problem, our first example, guys, we kind of skipped the last step because we didn't have to do anything. What's the fourth step say in our process for finding empirical formula? Multiply, right? Does it say round? No. All right, we do not round here, guys, when we get to this point. We multiply to get to a whole number. Okay? Again, it's a ratio. If we can't just round something, then now, you might be thinking, well, we do that in the last one, 3.02. Yeah, if it's that close, guys, where you have 3 or something, 0.0 something else, that you can round. But if it's anything else, like 0.5, you can't just round. That's a huge difference in terms of atoms. All right, so we have to multiply. If you take a look at your notes, if you end up with one of these decimals, folks, 0.25 or 0.75, we multiply by 4 to get to a whole number. It's like saying, okay, I have a quarter or 3/4, right? When you clear a fraction, you multiply by the denominator. That's why we're multiplying by 4. 0.33 or 0.66, we're going to multiply by 3. 0.5, we multiply by 2. We're trying to get it to a whole number. So in this case, my decimal that I have there is 0.5. What am I going to multiply by? 2. Now, am I going to do it just to that one? Right. Why do you think we have to do it to all of them? Not that we make it even, but what are we looking at? An empirical formula is a what? It's a whole number what? ratio, guys. If you change up one thing, you're changing the ratio. You've got to do the same thing to all of them so you have the same ratio, that same comparison. So we have 2 Ks, 2 CRs, and how many oxygens? 7. All right? So we multiply to get to a whole number. So my final answer is going to be K2, CR2, O7 is my final empirical formula. I'll give a prize. Whoever can raise their hand and tell me the correct name of this compound. It's a whole big process. Is the math that difficult? Is it anything really different than what we've already done? No. It's just putting it all together. Remember the whole process. Claire, you got a question? You got it? So, to help you remember the whole process, guys, there's a saying, there's a little rhyme here. And it does actually rhyme, all right? It's something that you want to commit to memory because you can write this down on your test or quiz, and it's going to help you remember the process to get to an empirical formula. So the first step is percent to grams. You should write this down in your notes at the bottom where you have space. Percent to grams. I'm sorry, no, not to grams. There it is, percent to mass, which is going to be our unit, is going to be grams. Percent to mass. Mass to mole. Divide by small. Times to whole. So you put it together, percent to mass, mass to mole. Divide by small, times to whole. There's your rhyme of the day. All right, it is cheesy. You might say I have bars. Isn't that a thing? Look at that. And I actually recorded that too, so it's going on the video. So, there's our process, guys. It's nothing really new. It's just putting everything we've learned all together in one step. All right, kind of one long process. All right? So, let's dive into another one. I want you guys to try this one on your own. So, folks, a lot of people get to this point in the problem. They get to moles fine, and then they're like, okay, well, then I just round it or I multiply here. You've got to remember the step. This is the one that most people forget. Dividing by the smallest number of moles. So here we got to divide by 1.09 first. All right, so that one on the bottom here with phosphorus is going to be 1. Calcium is 1.5. Now is when you will multiply to get to a whole number. All right. We're going to multiply by 2, each of them by 2, so we get 3 and 2. So that's how we get our final answer of calcium 3, phosphorus 2. So calcium phosphide is what you should end up with. All right. Don't forget to divide by small. It's a crucial step because if you were to just leave it with that 1.64, that's a lot harder to get to a whole number. That's where people get really crazy subscripts. If you get something that's crazy, that's like super huge, you've most likely done something wrong. You guys are going to work the next U-Try problem in those 3 that are on the bottom of the page there. All right. If you have